that it's a directory. So when you unzip it, you may not see anything. Wherever directory you unzipped it in, go in there and there'll be a directory called view. Okay, and I'll show you what it should look like. And this is, so you're not actually seeing my screen yet, are you? So, or
somebody
now,
said, Joe, that they didn't see the zip file yet.
Drop that in there one more time.
Does anybody else see it? Jonathan, do you see it?
Yeah, I see it. It says new.zip,
Okay.
right?
And if they joined right after I dropped it in, they won't see it. So we'll have to give it a few minutes. And
it seems like a lot of people don't see it.
Okay, so Jonathan, how many?
There's like all right. I don't have to count one by one. One, two, 3, 4, 5, 6.
Can you drop it back in, Jonathan, or no? You need me to.
Let me download the zip and I'll see if I could drop it back.
Okay. I mean, now it might have gone by already. It's in the chat as everybody's talking. It might have gone by you.
Let me save it to my desktop.
They said they cannot see
that might be part of what's happening.
Let me check it out right now. I'm gonna see if I can drop it off.
Oh, you're right. Very good. Pick up, Eric. I didn't realize that was just sending the host and panelists.
Oh, look at you, Eric. Thank you for saving the day.
Thank you.
All right, I think I sent it. Oh, Eric, you did the presentation. And you were also a cohort. Somebody I met at the cohort. Yes.
Eric, your name sounds familiar. Okay, is that better?
New York cohorts represent. Yeah, they should got. I think when I sent it.
Yeah. Yep. I accidentally just sent it to the host.
Yeah. So we're good to go.
Okay, just give me a second. Tune some stuff around. Okay, you should see directory, and you won't see any of that because that's not the right directory. So let's see. Let's go to documents and in here somewhere. Oh, I mean documents. So you should see something that looks like this. You should see this. Okay, Jupyter Notebook and 3 data files. This directory is empty. It wouldn't let me delete it. Apparently, I have some ghost script somewhere sniffing that bad boy. So I couldn't get rid of it. Sorry. But if we are good to go, Ms. Corey, are we good to go? I'm not sure if she's on. Corey, are you recording? Anybody there?
I think I don't know. I think she started recording in the beginning, so we should be good.
Okay, we're good to go. Welcome. We are going to be talking a little bit about machine learning, and I'd like to introduce myself. My name is Joe. I am an instructor at Flatiron in the data science program. With me tonight is Jonathan, co-host. He is a graduated about 2 weeks ago from Flatiron. Extremely knowledgeable about machine learning. Did an amazing job on his project. Helps everybody on our Slack channel. So Jonathan is amazing. So Jonathan has joined. He's going to help answer questions and be sure I don't give find people too many wrong answers. So I am using Jupyter Lab, not Notebook, which is exactly like Jupyter Notebook, except a little more powerful. Up here on the left, you can see some of the things we'll be covering. Okay, we'll obviously, as you know, be talking about World Series data. This is a whole mess of libraries we're going to be loading. I don't use all of these. I've lost track of which ones I'm using and not using. So I'm terrified to delete any of them because I might need them. Okay, so what we're going to start off with is reading our data. And there are a couple of different data sets we're going to be using. One is a bunch of data on postseason and the results of the postseason. And Jonathan, I can't remember that file goes back to 1800 or something, But
yeah, I think it went to like 1871 or something like that.
Yeah, something like that. And if we wanted to look at it just to see what it looks like, 1884, there's a round, a team winner, a league of the team winner, a team loser, the league of the team loser, and the number of wins, and so forth and so on. Okay. So this is what I'm using as the source for the postseason. Okay. The problem with this, as we're going to learn later, is in machine learning, it is built on the idea of having some consistency, and the different rounds come in at different times, so it kind of hampers us in terms of what we can do and what we can use in terms of trying to get some good results from our model. So we'll talk about that in a little bit. So it turns out I needed to limit myself to 1995 and later. And the last year we have 2021. And we're only going to consider these rounds, okay? And because we're only considering the championship series and the first round and second round, we're limited to 27 years. If we were to go back up here and let's see, what's the best way to do that? Do round dot value count. So if we look at the different rounds that are in our data file, okay, you'll notice there are 124 World Series, because they've always had World Series, except in the years they haven't had baseball. Okay, but these other rounds started later. So at the beginning of our data, there was only a World Series and only 2 teams made it, and they went off and decided a champion. And then at some point, they included the ALCS, and then later the ALDS is 1 and 2, and NLDS is 1 and 2. So, you know, when we're doing this project, we had to decide where we want it to be. Obviously down here, choosing these, there's just too little data to be effective. And I felt, and my concern was that just using the World Series, even though we have 124 years of it, tried to pick a World Series winner out of all of the teams available, though might be very interesting, I was worried that the model would have trouble, because our categories of winning the World Series and not would be extremely lopsided, with 30 or so teams not winning it most years and 1 team winning. So that makes our modeling problem a little harder. So because of all these things, I've decided to limit it to this part. And the first idea was, again, it becomes so lopsided to just try to pick one winner out of 30 or 31 teams over 27 years. That'd be interesting, you know, if when at least when the playoffs start, if you do the playoff teams, you could pick a winner. That would still be useful, and in terms of betting on baseball, you could still make a lot of money that way. If when the playoffs started, you knew who was going to win. You could also win a lot of bar bets with your friends, or side bets with your friends. However said. So what I'm doing here is I'm limiting to 1995 to 2001. So those are the years that these rounds occur. This said 27 rounds occur, and it'll obviously include those first 3 up there. So I'm limiting my data a little bit, okay, because of the constraints I mentioned. I also have seasonal data. So what this is going to give me is seasonal data on, for each year, what the seasonal totals were for each team in terms of offense and defense. Okay, including things like let's see, someone's here. I want to see runs you scored, at bats, hits, and then things like anything with let's see, I think it doesn't show them all, and I'll show some of them in a little bit. So I'm picking out, here it is right here, the features we want to look at which are just numeric features, okay, except for the team ID. Okay, so R is runs, AB is at bat, and then anything that ends with an A are the team you're playing. So that's against. So R is how many teams you scored that year, and RA is how many runs, how many runs you scored that year. RA is how many runs you gave up that year. So it does it for the total year. So the idea is when the playoffs start, we have a team's total statistics for that year of the playoff. Could we use that to predict who would win the World Series? Everybody with me so far? So
yeah, Joe, can you scroll in a little bit so they can see the code a little bit better?
A little bit better? Absolutely. Yeah. We'll try.
Thank you.
Got a little bit better? Okay, and you have the notebook. So, unless you don't have Jupyter, that's right. Okay, so we are limiting by some of those things. Okay, and here I'm just taking a check of my data now, what I have separated out to be sure it looks right. So this is just a sanity check of what I have. So now what I have is a set of data that has, let's just show this real quick. And actually it's right here, isn't it? Do a print on this bad boy. Okay, so this is what our data frame looks like now. The year, the round, the team winner, the league winner, the team loser, and then how many games the winning team had, and obviously how many losses the losing team had. Okay, so that's our first data frame in terms of just the playoff winners. Remember, we have two data sets, one with the team statistics and one with just the playoff winners. So right now I'm separating out my playoff winners because this is going to form the backbone for what I want to predict, the target. Okay, and it is generally called the dependent variable, because this is what's going to be. We're trying to say that who wins the World Series is dependent on these annual stats that each team has amassed. So right now I'm working on building that. So what I have here is I'm building who won the World Series. I'm sorry, I'm building now who are the playoff teams. Okay, so this tells me for every year who the playoff teams are so that I can just use that in processing. This is where, at least for the first round, okay, I am building my dependent variables and my independent variables. So again, so now in this case, my independent variables are what we're saying, these are independent and we can use these to predict the target. So what I'm doing is for every year, I have data for every team and I don't need that. All I need is for every year, I only need the data for the teams that made the playoffs. So I'm separating those out, okay, into pandas data frame. So I have that. And then I'm also creating, that is being stored in traditionally what you do in a variable called X, capital X, in data science is kind of traditional. That's where you put your independent variables. We also call them features, okay? And then I'm building another variable called Y. That's going to be my target. That's going to be the result. What I want are my Y and my X to line up right so that I know that in this first record, this is for the data for a team for 1995, and that in my Y list, this is the results for that team, okay? So at this point, once I've run this, what I now have are all of my independent variables. They're going to be used to predict my dependent variables. And this is what my dependent variable looks like. So what I've started off with is, when the playoffs start, can I just simply predict the World Series winner, okay, out of the variables I have and using the features I have. So I have one set of variables that are my features, going to be used to predict, and I have one set of variables with the result. This is what I want to predict. And you notice these are what's called a binary classification. I'm either predicting that it's a 0 or a 1, it's a true or a false, okay? And the true is that team won the World Series, and the false is in that year of the playoffs, that team lost the World Series. And for every World Series, there are 8 teams. So there are 27 years. So 27 times 8, somebody do the math, 160 and 56, 216 or something like that total is how many I have for the 27 years. Something like that, Jonathan. That sound about right? Close enough? Okay. So
Close enough.
The first question is this even doable? Can a model even come anywhere close? If you have any experience in data science, you used to people talking about train and test and doing predictions and all of that. And that's good when you get a little further down the line. But here's my question. Can I even come up with a model that can even sniff getting any of this right? Is it even going to be close? Okay. So that's the first thing I'm going to do. I'm not going to try to make predictions. I'm not going to try to do a lot of other stuff. Can I even analyze the data correctly and get that right? Because if I can't do that right, then there's no reason to try to predict anything. So in a way, this is a first step sanity check, okay? And the first model is one of the simpler models in terms of doing so again, we're going to be doing a classification. We're trying to classify whether you're a 0 or a 1. And one of the earlier and simpler models is called logistic regression, okay? So what I'm doing here is I'm building a logistic regression model, okay? And then I'm going to fit it. And what fitting means is you're going to train it. You're going to take the input data and see if you can predict the output data. And that's what this step does. This step builds and trains your model. Now, I'm using all my data to do it because I just want to see if this is even possible. Okay, so I run it and fit it. I get some nasty things about iteration limits, but right now I'm just doing an exploratory step. And then I'm going to get a score. So my score is 88. So it means 88% of the time I'm correct. So who thinks that's good? Okay, I'm predicting the correct winners or losers 88% of the time. How are we doing on the chat, Jonathan? What are we getting?
Somebody said that's good, very good, maybe, so on and so forth.
Okay. What do we got?
They say it'll earn a profit.
What's that?
Somebody said it'll earn a profit.
So somebody says we'll earn a profit. Okay. And generally, when you look at something like this, you would think you're doing very well. Okay. So, but remember, we're only predicting 0s and 1s. Okay. And the truth is, the one you mostly want is just the 1. You really just want to know who won the World Series. And there's a very small percentage of that, 1 out of 8. Okay, so somebody divide 1 out of 8 for me. Guess what you get? About 12%, I believe, right? Somewhere a little bit more than 12%. So we have an accuracy of 88%, which means we're missing about 12%. So let's see how we did. So we can plot what's called a confusion matrix, which shows us, it takes a second to get your mind around, but this is what we're going to be looking at, okay? So the bottom is what our model is predicting, and the left here is what the truth is. So remember, we have a 0 or a 1, so there are a actual 188 truths, okay? And there were 4 falses. So our model predicted 188 true values correctly. It predicted 4. Sorry, these are falses. Correct me, Jonathan. Are you listening at all? Help me out,
sorry. I'm paying attention to the chat. I'm paying attention to the chat. I'm sorry.
Okay.
Trying to answer.
So
okay.
I got it backwards. So
yeah, sorry.
Are the falses. So
the zero.
I predicted 188 correctly. That's what this box says. So I predicted a 0, and it actually was a 0.
Yes.
I predicted 188 of those pretty good.
So that means that we predict the 0 represents that, the people who lost the World Series. So we got it right 188 times.
Right. So
out of 189 times essentially.
And we predicted 4 winners correctly because we predicted a 1, which was a winner that actually was a winner correctly. But we predicted 23 wrong. What's happening is the model is just predicting almost all of them to lose, it looks like your model is doing right because the majority of them lose anyway. So your model is not doing all that great. Okay, and this is logistic regression. So even though our accuracy is good, okay, we could just guess a 0 every time and get this accuracy. And that's basically what the models do. So in the long run, that's actually not all that good. Okay, and again, this is a lower end model, logistic regression. One of the better models, yes.
Sorry, I just wanted to say something. So for those who say the 88% was good, yeah, it is good if you look at the numbers just as 88%. But if you really look in more detail, you can now see that like 88% is not really that good because 88% for the wrong side. So we want to make sure we get that 88% on the other side with the ones that we're predicting correctly, not just overall predictions as a whole.
Right. And the reason this isn't good is you could just guess a 0 every time and get 88% of them correct. Okay. So as opposed to just guessing a 0 every time, we did exactly that. So that's why even though the results look good, they're not, because just by guessing that everybody lost, and we know that's not true, but there was never a World Series winner, we'd be right 88% of the time. So basically, our model shows 0 skill at picking out World Series winners so far. So we're going to try a different model called a random forest classifier. It's generally considered one of the better ones at doing this type of task. Okay, we haven't changed anything. Can we do better? And lo and behold, our random forest classifier can pick out 88%, 100% of the time. So we are right 100% of the time. So this model is doing much better. Woohoo! We're on our way. We found the model. And at least in terms of analyzing our data, it's always right. Was able to pick out 27 World Series winners. Was able to pick out 189 World Series losers. And remember, this is at the beginning of the playoffs before a game's been played. This model can easily pick out who won and who lost. And we're doing that seems pretty good, right? So okay, that's promising. Let's put this into a little more motion. So we know our model is doing pretty well analyzing our data. Let's see how well we can do predicting. So this is where we're going to split our data into one set for training and then one set for predicting. So the train data is going to be used to do kind of what it says, like we did earlier. We're going to train our model on it, okay, and see how well it does. Then we're going to actually use it just to predict value, see how well it can predict data. And we're going to keep track of how both of those do. So we're going to split the data about 70% into training and 30% into predicting. And generally, you use somewhere around 75, 80%, 70% to train, 20, 30% to test and predict. But every problem is different, and every problem has its own set of circumstances. So that's just a general rule, a general guide. So now we're going to create our model, and we're going to fit it. Okay, but now we're going to plot the statistics for the training. Then we're going to plot the statistics for the testing and see how it does. Okay. And let's see. So 132 and 19 and 0, 0. So the data, we correctly predicted 132 losers. And we correctly predicted 19 winners. So we've used 19 years of data for training. Let's see how we did testing. Ruh-roh, not so good. So we predicted 50 teams would lose, and they did. We correctly picked one World Series winner. We incorrectly said 7 teams won the World Series, but they did not. And we incorrectly said 7 teams lost the World Series when they actually won it. So the problem becomes a little hairier. It's not quite as easy as we had hoped. We can train our model really well, but we're not getting nearly as good a result. And this is called overfitting. And the reason this happens is because our model is picking up features in the data that might only occur in that subset part of the data, but don't occur in the entire data set, or our model is just bad. Could be any number of things. So let's try a different model. We're going to try something called the gradient boost model. Let's see if we get better results. So again, we're going to create our model. We're going to fit it, and then we're going to check our results. Okay. So again, we are training perfectly. 19 winners, 132 losers, all predicted correctly. I'm sorry, all picked up correctly. These are not predicted. Predicting wise, we did a little bit better. Okay. We actually were able to pick 2 World Series winners. We didn't pick the losers. We didn't predict the losers quite as well. There were 11 teams we predicted won the World Series and didn't. And there were 6 teams that we said didn't win the World Series and they did. So that's not a good model. Now, what we have is a data set that is really imbalanced. Okay. 1/8 of our data is true, 7/8 is false, which means that's a classifier imbalance. So this light gradient boost is supposed to do better with that. This is not part of the normal library, sklearn. This is actually part of its own library I downloaded. So I decided, let's give that a whirl. Okay, so we create our model, we fit it, and then we get our result. Let's see how we do. Okay, and again, a lot of warnings. Good so far, 132 and 19. Like to see that. That's good. Row. Only 2 values right. And ultimately, this is the box I really care about, right? Because if I have a 7 in here, I don't really care about the others. Because if I have a 7 in here, remember, we were predicting 7 years, I believe. Or is it 8 years? Sorry, 8 years. So if I have an 8 here, then I'm happy. Woohoo! I can use my model. I can predict it. I'll be rich. Be living in Vegas. Jonathan and I will have pools in Vegas, and we'll be living on the high life. But this model ain't it. Okay. So one thing we've done is we've used the data as is. And if we scroll back up here and look at our data, we'll notice that there are, let's see, that I pass it out here. Where's our annual data? Maybe I didn't look at it yet. So here it is. If you look at this, let's do this a different way. Let's do this a different way. Let's add a little cell right here. And let's do x dot describe. So if we look at the data we're inputting, and what we see, let's see, you see counts and whatnot. You will see that there is a large range in our data, like top, I believe is the top value, unique of the number of unique values. What you will see is there are a large range in values for like run scored, add backs, hits, strikeouts. You know, those values can be anywhere from 10 to 1,000. So there's such a large range that sometimes that large range can cause problems when trying to use them to predict things. So what we do is we scale the data by bringing those ranges, the differences all down to something that's much smaller, and we scale the data. So maybe that's the problem. Maybe we haven't scaled our data. So we're going to what's called scale our data so that we don't have such large ups and downs in all of our different values. The changes in the data will be very small. Let's say if scaling our data helps any. Okay, so now we're going to scale the data. Then we're going to use this scale data to train our model, okay, and to fit our model. So let's see if that gets any better. So again, 132 and 19. Again, this is our train, so we're still doing good. Predicting, we're not doing any better. Okay, we're still only getting one World Series value right. Okay, so let's try X boost, which is another model. Let's see if that helps. See if we get any better. So again, 132 and 19, that's a good start. Oh, this is even worse. We don't get any right. Okay. So I'm going to save these other sections. We're going to come back to these because this is the order I did this project in. Okay, I came back and added these sections, and you'll see why later. So we're going to skip these two for now and come back. So we're adding data, okay, and we're trying to predict only the World Series winner. And maybe that's the problem. Maybe our classes are just too imbalanced, okay? And trying to pick out just the World Series winner is not a good idea. So what we're going to do is, instead of picking out just the World Series winner, we're going to create a new set of classifications where we're going to encode our data by how far you got in the playoff. Okay, and that's what this code here does for us. It's going to encode the data, code the data, okay, and show it. So in 1995, Atlanta won the World Series, so they're encoded by the number of values, the number of games they won in that year's playoff. So Atlanta won the World Series, so they get a 3. Cleveland lost the World Series, so they get a 2. They won 2 games, okay, but lost in the World Series. Seattle and Cincinnati won their first round, but lost the second round, so they get a 1 each. The teams that didn't make it out the first round get 0 each. So now instead of just trying to predict a 0 and a 1, what I'm trying to do is I can't get my models to do better. I'm gonna what's called feature engineer. I'm going to change my data a little. I'm not actually feature engineering. I'm actually changing my target from target engineering to see maybe if I could do better that way. This is all part of being a data scientist. It's not just about picking the model. It's how can you arrange your data better that it might do a better job. That might include creating features, or that might include changing your target. In this case, I'm going to change the target. So instead of trying to predict a 0 or a 1, I'm going to try to predict a 0, a 1, a 2, or a 3. So I'm going to try to predict each team's results for that year. You still with me? That making sense? Jonathan, we still good?
Yep, we're still good. We're still good. We're still good.
Oh, cool.
I actually like this. I like this. The way that you actually categorically encoded.
So yeah, this is just trying to get some kind of decent result so I can move to Vegas. I don't want to move to Vegas too hot. I live in Denver and I'm happy with it. Okay, so I have created a new set of data, and I'm going to apply that to my Y value so that now what we see are we have 108 zeros, 54 ones, 27 twos, and 27 threes. So what I'm doing here is a sanity check. And I'm just becoming more familiar with my data. So there are 27 World Series winners, a 3, and there are 27 World Series losers. That's good. That's what we should have. We have 54 teams that won 1 playoff round. So that sounds right. We have 108 that have lost. So this sounds right. Okay. So let's see if we can get better results. So we are going to train, test, and split, but I'm going to try my a slightly different method. So earlier I split the data myself. I kind of like to control that, but it's not a random split. I use the first half of the data to train, and I use the second half of the data to test. That could be the problem, right? So I'm going to use a method called train, test, split that will split it randomly. And we give it a random state so that Jonathan and I are working on the same model and we want to use the same data. If we give it both the random state of 42, we will get exactly the same set of random data back. So that when we're working on the model, the problem isn't that we're using slightly different parts of the same data set. We're using exactly the same data set. Now, in data science, the question always is, why do we use 42 as the random state? Can somebody put that in chat? Why do we use 42? And random state can be any integer that I know of. But we use 42 a lot. Who knows why? Anybody coming up with it, Jonathan?
Yeah, somebody said the meaning of life.
The meaning of life, absolutely. Data scientists, we don't have much of a sense of humor, but we do have a little one. The meaning of life, okay? You can use any number in here you want. You're gonna see a lot of examples of 42. Now you know why. The other thing I'm doing is I was using 70% for my train test split. So now I'm using 60%. I'm training fine. I'm training amazingly, but my prediction is not doing so well. So maybe if we have a little more data for the prediction, maybe that would help. And then when I split, I'm also going to go ahead and scale, because it generally never hurts to scale, okay? So let's try this problem. We're going to use, again, the XGB classifier. I have read good things about this, okay? Let's see how we do. Now, remember, we don't have the 0 and 1. We're now predicting 4 values. So we have a confusion matrix 4 values. So as a analysis tool, this thing is working amazing. It's picking everybody out right. 10 World Series winners, 7 World Series losers, or 7 people in second place. So remember, this is a random pick now. When I did mine, the numbers matched up. This is a random pick, okay? So these winners and losers aren't going to match like they did last time. We have 26 correctly picked people who only won in the first round, or teams only won in the first round. And we correctly predicted 43 teams, or correctly picked out 43 teams who lost in the first round. So our analysis is going well. Our predictions, not so well, okay? We only picked 1 World Series winner correctly. We picked 3 World Series losers correctly. And we only got 8 teams correctly that won and lost in the first round. 46 teams that didn't win at all. But look at all of these numbers that show how many things we did not pick correctly. So a World Series winner, we picked 1 correctly, but we picked 3 incorrectly. So we said 1 team won the World Series when they lost the World Series. 1 team that won the World Series that only made it to the first round, and 1 team that won the World Series but lost in the first round. So we're still not doing that great, okay? So this XGB classifier has a max depth. So I said, let's change the max depth to 8 and see what we get, okay? It's the same model, we're just gonna try something a little different. Again, we're doing everything perfectly on the analysis. We're still not doing any better, okay, in the model itself, or in the predictions themselves, which again is really where we want to be. So that's not good. So we're going to look at one. MLP classifier is kind of a special deal. It's actually a neural network with a single point call interface, okay, which is really cool. It gives you the ability to run a neural network without having to do all the steps to set it up yourself. This hidden layer size tells it first number of how many neurons in your neural network, and 6 is how many layers, okay? And a neural network is called a neural network because it kind of works like your brain. It has a bunch of different nodes that all feed into the next layer of nodes. So I'm defining how many nodes I want for 30, and then how many layers for 6. Okay, this is what you're going to see here is the best classification. I ran this thing about 35 times last night with all kinds of different setups, all kinds of different attempts to see what kind of results I could get. You can do this with something called a gridding network call, where you can input a bunch of stuff and it'll tell you what was the best. One of the reasons I kind of don't like doing that is I find I learn a lot as I input some of these values and see how the model reacts compared to how I ran it last time. Tells me a lot about the data and the model. So where grid search has some amazing features and stuff, I like to kind of get more feel for how we're doing, okay? So again, we're not, and I'll say again, now we're we're not training quite as well, okay, because we did miss some training. Maybe that's a good sign. It turns out that our model did get better. We did wind up predicting six World Series winners correctly, but we also predicted 12 incorrectly. Okay, and in fact, there's more than that. It's actually 21 incorrectly. So even though we weren't able to pick out 6 more World Series winners, so far it's the only model that has even gotten above 2. Okay, we still have a lot of features in here. Now I noticed that this is telling me that this model actually didn't complete running. It quit because the number of iterations it'll run and try to get the right answer is randomly set as default as 500. So I'm going to kick this up to 1500, and Jonathan's going to freak out saying this is going to take forever, but not on supercomputers here.
Yeah, I mean,
it's not fast. So did we do any better? And we did not. We're still only picking out 6 winners, and we're still getting the max iteration error. So now it's making me mad. So now we're going to crank this bad boy up to 3000. See how it likes that. That took it a little bit. There we go. That got rid of that error, or that warning. It's not an error, it's a warning. We're still only picking out 6 winners. So, okay. So we're still not doing well. But maybe the problem is, I mean, we're still doing better than the binary classification. We were able to pick out 6 winners. So maybe the problem is that what we're predicting are this set. So maybe instead of trying to predict the World Series winner, what if we could just predict the 2 teams that got to the World Series? Because if at least you can predict that point at the beginning of the playoff, if you can limit it to 2 teams, you have 2 options. You could run another model to try to pick those 2 teams and do better, or you still have a 50-50 chance, okay, at the beginning of the playoffs of picking the World Series winner. So if we can at least do that, so we're going to we're going to target engineer again. We're going to change it slightly, okay? So we're going to change it so that we can get, instead of just World Series winners, now we have, instead of 27 winners and losers in the World Series, we have 54 teams that made it to the World Series. We have 54 teams that lost in the first round and 108 teams. So what we've done is we've made our data simpler so that maybe the model can pick these features out and predict them better. So sometimes when you're overtraining, your model is overtraining and overfitting, what you do is you either make your model less complicated or you make your data less complicated. I don't like making the model less complicated, because the way you do that is you don't bring up your prediction scores, you bring down your analysis scores, and that don't help your prediction scores at all, okay? That just makes me mad. I don't like the idea of getting better by getting worse. I want to get better by getting better, okay? So I rarely, if I'm overfitting, I don't like to make my model work. I like to find a better way to do it with the model I have. So let's see if we can do better, because what I'm saying is by changing and making the model less complicated, we're not going to bring this 6 up. We're going to bring how we do up here down, okay? And that's not going to help us bring 6 up, okay? So if I'm betting and wanting to win, then that's just not the answer to me. So let's run this model, okay? So again, we're running it. We have changed what we're trying to predict. Can we do any better? Okay, so again, now instead of predicting 4 values, we're only predicting 3 values, 0, 1, and a 2. So again, our analysis is getting a little worse, because now we're predicting 13 teams that lost and they actually won the World Series. But this is the analysis, so maybe, just maybe, we'll do better. And we're not, okay? We're only picking 3 correct teams to actually get to the World Series. We're incorrectly picking 8 teams to get to the World Series when they lost in the first round. That's really bad. We're predicting 17 teams to lose in the first round and they actually got to the World Series. So we made our data simpler and we still didn't do well. Maybe random forest classifier will help us, okay? So maybe that'll just do a little better. So that's one of the models we ran earlier, okay? Well, this is promising. At least the analysis is looking good. And it turns out we're not doing horribly. We're picking 5 teams. We're doing better than this one did, okay, in this particular round. So now we're picking 5 teams correctly to get to the World Series. We're still picking 22 teams that got to the World Series, and we're saying they lost in the first round. So that's not good. So there is a technique called smoke, where when you have data that is imbalanced like this, what you can do is you run a technique where it takes the imbalance class, the one that has the least, and it adds data that replicates the the category with the least count to try to bring those up to see if your model can do well. So here, where we have a bit of an imbalance in our train, we're going to smoke our data so that we have a more representative set of data, okay? And when I shouldn't say representative, I say classes that are more equal in count. This can be useful at times. It's not my favorite technique. I'm never a fan of replicating. Jonathan, you have a statement?
No. Somebody asked me. I had to smile because somebody asked me if I had any coding experience before I started, and I was just like, I had zero, like absolutely zero.
And a lot of our students don't have a lot of coding experience when they come here. The program is built for that. And Jonathan is an amazing data scientist now. And I wouldn't say that just because he was my student for a short time. He was an amazing data scientist, which is why he's been asked to be on the panel. Okay?
Yeah.
So
Joe is being modest. Joe is being very modest, but continue.
We didn't do good, Jonathan. We voted and we got smoked. We didn't do good. Okay. So what if we go back to 4 classes? Let's try that. And we'll smoke. Because with the lower classes, you wouldn't necessarily expect smoke to help because you're not that imbalanced. Okay. And this is really for when your data is imbalanced. So let's try that. Okay. So when we smoke with the 4 classes, we still don't do any better. Okay, so we're not helping our case. So the problem is, we don't have a lot of data. We only have 27 years. And this is a particularly gnarly problem. If this was easy to predict, there'd be a lot of really rich people running around right now, and Las Vegas would be out of business because everybody would be taking them for money. So let's try a different path. And Jonathan has seen me give a class on this last time. On our last thing, and I was hoping this was going to work out, and it turns out this didn't work out like I expected either. So we're going to go back to gradient boost because that wound up doing some of the best. Okay, and what I want to do is I want to look. What it should be able to tell me is which features are the most important in terms of making our predictions and our analysis. And if you can figure out which of the features are the most important, you can at least gain some insight into your data. And I thought we would get something different than we got here. What you notice is these numbers on the left don't really mean anything. What they mean are they're relative. So the higher the number, the more important it is compared to all the others. And our model is saying that doubles, 2B, or how many doubles you hit, are the most important thing to getting to the World Series. And pitch out are the second most important thing. Anybody who knows baseball probably knows that I'm not a big baseball fan, but I'm fairly certain how many doubles you get isn't the most important thing to getting to the World Series. My guess is it would be either runs scored, hits, hits by the opponent or runs by the opponent. You would think those might be, but okay, so maybe it's this particular technique that's not any good. Research told me that this particular technique for feature importance may not be great. So I tried the permutation feature importance. It supposedly might do a little bit better in this type of problem. And we found out that that's even worse. Okay, the second base hits are even more important. So that's not good. But let's play along. Let's say maybe the feature importance know what it's talking about. So what I tried is maybe I'll get better results if I just use the features that are important. And the truth is, in most cases, it shouldn't make a huge difference because your model should be smart enough to ignore the ones that aren't important. But sometimes you will see an improvement by limiting features, and it's called feature selection. Okay, you know, a really smart model should limit features that aren't that important. So I'm going to take the 5 most important features. Okay, and I'm going to come down here, and I'm going to see that that didn't help at all. Now I got no World Series win. So I ran a bunch of different cases saying, okay, if these second base hits are so important, let's run with just them. Okay, when I run with just the second base hits, I don't really do any better. I'm still only picking 1 World Series winner. So maybe it's not just second base hits. Maybe it's just the offensive stats, okay, that are important. So I ran with just the offensive stats. And lo and behold, I did get 6 winners this time. Woo! I still got 18 wrong. So not great. Okay, so maybe it's not the offensive statistic. Maybe it's the, oh, this is everything again. I was just wondering what would happen if I just ran everything again, and nothing. So now I'm up to 7. You know, again, 11 wrong. I had 6 right last time. So, okay, so this is not working. Now remember when we did the first thing, okay, where we were just trying to pick the World Series winner. We said we were going to go back to that. So I learned some things in here going through all of this that piqued my interest a little. First, the idea of smoke. I didn't really expect smoke to help in these particular cases because our classes aren't imbalanced all that much. But in the other case, they were really imbalanced. Okay, so I'm thinking I want to try smoke. And then the other thing I didn't try is the neural network classifier. I didn't try that in the other case either. So what if I smoted and used the MLP classifier at the same time? So I'm going to go back up there. Okay, this is where we were. So I'm now going to open up this part of my notebook. And what I'm doing is I'm resetting all my data because Jupyter Notebook remembers everything. It doesn't go by where you are. And if you go back up to a cell, it remembers that cell's data. Okay, Jupyter Notebook remembers the data from the last cell I ran, and if I come up here and run, that's what it's going to use. So I have to reset all my data to be sure I'm getting what I want. And what I mostly want, right, is I want the 0 and 1 binary classification, and that's what this loop is setting. So instead of, again, trying to play out, I want to try the data first with the MLP classifier to see if I can get any better results. Okay, so that sets up my data. Then I'm going to try the classifier, the neural network classifier, to see how I do. And I noticed in training, I'm not doing well, not that well, and in fact, in predicting, still not doing well. So that didn't help. But remember, we talked about that we're going to try the smoke. And the reason is we're going to do a different model, a GBR smoke, because our classes are really imbalanced. So if I add a thing here, we can counter on our, let's see, do we have our Y value yet? So we noticed before we smoked that there are 189 zeros and only 27 ones. So that is really imbalanced. So the idea of smoot is it's going to create data, okay, by adding to this column. And what I have done is I have set up my smoot, and then I have said smote me, okay, so that if we were to also print our y, if I could type, let's see, which one am I? Let's see, I need to change this just a little bit. I showed all of y, but I'm not smoting all of y. I'm only smoting the string. Okay, this one. So the original that I smoted was, it had 132 zeros and only 19 ones. So what it does is it creates it. What's the word I'm looking for, Jonathan?
It creates like synthetic data, and it
Synthetic
gives,
data. Yeah.
yeah, and it gives the data, like, it's essentially guessing where the data might be in a sense. Yeah.
Yeah.
To make it more balanced.
So now I have 132 World Series losers, and it adds in 132 World Series winners, and it synthetically creates the X data to go with it to see what we might get and if we can get better results. So we're going to use the gradient boosting classifier because if we look up in the binary classification, it did the best. So that's why we're going to use that model. And we still haven't done better. So at this point, I would claim that this is just kind of mostly not modelable. We've tried a ton of different techniques and a ton of different options, and what we learned from this is not every situation is modelable. And when you're modeling something, what I like to tell all of my students is the first thing you should think of is the system you're modeling. You're not modeling a collection of data in a black box blindly. You're modeling a system. Is that system predictable? The example, are solar flares predictable? Probably not. It's a totally chaotic system and totally random when a solar flare occurs. There may be more solar flares at a certain time, but you can't predict when an individual solar flare will occur. So when you're modeling and doing machine learning, the first thing you should do is think to yourself, is this system modelable? And it turns out this particular system probably is not modelable in this particular form. Now, there are countless numbers of ways we could change our data and change our models, and we could do lots of different things to get better results. One thing I would like to do next is actually take head-to-head in the playoff, each team head-to-head, and try to predict the winners that way. That's a totally different animal there because that involves what's called a Siamese network, where you compare the scalars of the two teams or the vectors of the two teams and decide which one is greater than the other. It's definitely not something we cover at Flatiron. That's a fairly advanced topic. There are no sklearn Siamese network setups. You actually have to set it up yourself. Everything you've seen that I have done, we teach at Flatiron. Every technique you've seen, we teach at Flatiron. So I didn't want to go outside of that too much. It gives you an idea of what it's like. Hopefully gives you a little bit of an idea of what being a data scientist is like. And the kind of the approach to the problem in terms of starting with a problem. First of all, seeing if it's even modelable. My analysis, was pretty good. The model training is excellent. The model predicting is okay, not working well. But one thing you can do, if I had gotten features that looked a little more reasonable, what I would have done was I would have used those features to change the data itself to see how that affects the outcome of my prediction. And for example, I can run an analysis model that will take that data and predict for that year how many games each team won within one game for every team. I can't predict it, but the analysis can pick it out. I can then go in and change the features like how many runs would the Rockies have to score in a year to actually win more than 75 games, because that's what they're going to win every year. So if I do that, instead of 850 runs, if they could score 1,000 runs, they would get another 12 wins. I can then tell the GM what they need to do. Go out and get somebody who can hit the ball. Maybe pluck a few over the fence. You bring in people into the seats and you'll win more games. Might have to spend a nickel. The Rockies don't like to do that. So, any questions?
Yeah, it's, Joe went through like a lot of the process. Oh, somebody says the Phillies gonna win.
Notice I did not bother predicting the 2022 season. Why is that? That's a good question. Who can tell me why you don't think I tried to predict the 2022 season? Thank you, Eric. Well, it is a different playoff format, and part of the problem I'm fighting is you're right. They just put in wild cards, right? So I don't have enough data to train on wild cards, much less predict wild cards. But the reason I didn't predict the 2022 season is because my model's not any good. So let's say I predict the 2022 season and that team wins. Okay. Would I feel confident for 2023? And a lot of times what happens is people run a bad model and get some good results, and then they start trusting it when they shouldn't. And the moral of the story is my model sucks, so I don't trust it. So I'm not going to use it to make predictions. Hopefully that's not too blunt, but I like Jonathan knows I like being straightforward.
So yeah, like a lot of the process that Joe was going through are things that we do like to kind of figure out how to solve the problem. Like you choose different models, tuning parameters, checking different like if your parameters are imbalanced or is your target imbalanced. Do you like that's very, very important because one thing that like Joe was talking about earlier, especially with the imbalanced data set, is you can actually choose one of something and still get a really, really high percentage. So like me and Joe talked about this before, like when it came to like, let's say you have like some type of disease, right? And like you have 100 people, you're testing 100 people for this disease, right? And then you got 995 people correct, right? And then you have 5 people you didn't get correct. And it so happened that those 5 people were the people who actually had the disease. Then you kind of defeat the purpose, although you have a 95% accuracy rate of getting it correct, right? So it just depends on like how you're, you know, how you're approaching each and every problem, and with the data that you get, each problem is different and how you approach it. So yeah, that's why Joe was going through all the models, the XGB, you know, XGBoost, gradient boost, and random forest, and all these kind of things, because each algorithm takes a different approach to solving the same problem. So the cool thing I feel about data science is there's not just one way to solve a problem. There could be many ways to solve a problem. You just got to find the best. You got to find what you feel is the best way to solve that problem. So
Stanley brings up that he'd like to see a model that actually works. What we were asked to do is give a model on baseball, since it's the World Series. And if I had a model that worked really well, I probably wouldn't be given the workshop because I'd be in Aruba or somewhere having drinks on the beach.
Absolutely, I'm taking a cut too.
Baseball is really hard, and sports are really hard to model. And you don't see many successful ones because if somebody does have a successful model, they're not sharing it. They're getting rich. And Corey, that's a good point. So next workshop for machine learning, let's do something that actually works. For example, we can get around 70% accuracy on 70 to 80%. I think it's 84% accuracy on taking images that are X-rays, and about 84% of the time predict pneumonia correctly.
Oh, wow.
Okay. So maybe next time we won't do baseball because baseball's hard. Or we'll do the one I did last time where even though the model's bad, we can use it in an analysis technique. So next time we'll do something that's successful. So,
But I think
baseball
it's
is hard to
important for
predict.
people to see all sides of data science, right? So it's
Well,
like,
yeah,
this is one of those things, like it's not always an easy fix. And sometimes you have to go through multiple different like variations just to try to get to, to realize that it's not working. Like it
yeah.
is not giving you the outcome that you wanted to.
And that's the nature of data science. More projects do not work out in data science than work out. So that's the nature of the beast.
Yeah, so it makes it a lot. It's a lot of fun to do all that exploration. Like well, at least I have fun. Maybe I might be crazy, but like me and Joe are very similar in that aspect. We like to like explore like every possible realm of like whatever the answer could be.
I almost didn't go to bed last night. Every time I would try, oh, what if I smote it? Oh, that didn't, okay. What if I stand with smote it, turn around backwards and stand on my head?
And I think that this just shows like it's showing real life problems that you're going to face as a data scientist. Like it's not always going to be an easy outcome. So it's nice for people to be able to see the entire process and not just like, hey, this one works. Well, guess what? Not everything that you're going to put in there is going to work every single time. So there is definitely showing that like with every job, there's going to be frustrations, but there's also all of these other like great points about it where you can really predict things. And that's how, like you were saying, that's one of the ways that like pneumonia is being detected. There's the amount of things that are detected because of data science is just mind blowing as far as I'm concerned.
I'm teaching a class, part of a class right now for a company that has having 40 of all of their new employees learn a shorter version of what Jonathan went through, but it includes everything most of the things you saw today. And these are, I was talking to someone the day and they're like, I'm in finance. Why do I have to do this? And it's like, because data science is permeating everywhere and everybody needs to be familiar with it. You don't necessarily have to know how to do it. You better be familiar with what it can do.
Yeah, data is gold at this point. I mean, there's the stuff that we're going to be doing with data, and I I just keep reading articles about like how much we've been giving away for free that's already out there, just kind of floating around, and it doesn't ever go away. It's just there. It's there for everybody to pull and do stuff with. I mean, that's like I always use the example that's how that girl got targeted by Target and got what was it? She got pregnancy ads sent to her house.
Oh,
her family didn't know she was pregnant because of
Absolutely. In fact, so the true story is, Corey, that machine learning has been around since the 1970s and 60s. Big data has been around. I'm from meteorology. We've always could create more data than we could use. But it wasn't until the late 1990s that people figured out you could make money from it. That's when it really took off. And exactly like you said, Corey, some of the first things were in social media to use machine learning and whatnot to figure out what ads to show people.
And also like your shopping habits. So if you're always going online and looking at certain things, then they know what ads to send you, and that can
absolutely
bite you in the behind if you're not paying attention.
Absolutely. And a lot of people are asking like where to start. And the one thing is Python is a great language to do.
Yes.
Everything I did today was done in Python's Pandas, except the machine learning itself. All of the reading, cleaning, looking at, viewing, sniffing, all of that's done in Python Pandas. That's a great place to start because Python Pandas can then be fed right into the machine learning model. So if you're looking to get started, that's where I would start, learning Python and learning Pandas.
Jonathan, what was your experience with the whole prep work experience going into Flatiron? Because you get into a little bit of stuff before you even enter the program. So maybe just talk about that for a minute, because I think that that's important, because that kind of, you dip your toes in just a little bit.
So when I started, I had to do the pre-work. So like Flatiron had like a pre-work, right? And I was terrible, absolutely terrible. So actually, I failed the pre-work test, and then I had to do the flex program because because I I needed to take more time to learn. But it was also useful to show me kind of what coding was about in the first place, because like I said, I started with zero experience, and like I didn't know what a string was, I didn't know what a float was, I didn't know what an integer was. Like I was starting from really zero, and I was just doing terrible. But the pre-work actually like gave me a little bit of an idea. My coding still was pretty bad even when I started the program. So like I think I probably didn't get decent at coding until maybe like phase 2. Like I think
Yeah.
it took me a while to get used to. Like
Yeah.
I was good with pandas because pandas just makes everything easy, but like I was still like, even my coding, like I look at Joe's coding and I admire his coding. Like as much as he says, as modest as he is, like Joe's coding is actually quite amazing. I would love to learn to code like that. But when it comes to like the actual coding, like it's just a process. It's just something you have to keep doing over and over and over again, figuring it out, doing research, reading articles, watching videos. Like you have to go through all of it, just the growing pains.
It's a brand new language
Jonathan's
to
an
learn.
amazing data scientist.
But it's
Yeah,
also
yeah.
like, it's amazing to look at like how difficult of a time you were having when you were trying to start the program, and like where you're at now, and like how confident you are
Absolutely.
and how much you know. It's like that's how much you get to grow over your time with the program. I
Absolutely.
really appreciate that.
Absolutely. Like I don't think that could be stressed enough. Like where I started to where I am now is like so drastically different. Like I don't think I could look back at myself the same way at all. Like I sometimes, like when I'm coding, I'm looking at it like how didn't I know this? Like what was wrong with me? Like how did I feel that way? And then like how was I like that? But then like when I was going through it, I was like struggling. I was like, oh my God, what am I doing? Why am I subjecting myself to this? But
Every good program is like that. I mean, I went through this
yeah.
while I was doing my bachelor's degree. I was crying constantly. Yeah, Flex is, thank you, Joe. Flex is from 20 to 60 weeks. I think that everybody tries to keep it under 60 is like the maximum. So staying
Absolutely.
underneath that is usually a good idea, because you never know what's going to come up in life. Everybody is adults and you get curveballs all the time. So it's just really good to allow some flexibility. I'm actually in the product design flex course right now. So I am also in the trenches with everybody else.
Yeah,
Yeah.
the flex was good for me because it allowed me more time to learn. Like I was able to really like dive in deep into like really subjects, because in live things move so quickly. Like when you're in a live session, every single day is a new topic. So it's like it's good. The immersive it says that but does the immersive offer any advantage apart from speed? Oh, it offers a lot of advantages.
Oh yeah.
Like the advantage is that you're going through it with somebody. I think that's the biggest advantage, because as a flex student, like I was by myself and I was like driving my instructor crazy too. Like even with Joe, like I would message, like when Joe became my instructor, I messaged Joe pretty frequently. Like I'm like, Joe, how do I overcome this? Or like, what do you think about this? Or how do you approach this? And so on and so forth. But when you're in the live sessions, you actually have people with you going through it, and you also have your instructor as well, who has the one-on-ones with you, and they're with you in real time. With Flex, we have to schedule our instructors more than like with a live instructor. If you see them around, you'd be like, hey, I need to ask you a question, like, so you have that benefit. So it makes the speed a little bit more manageable. So
that's a good way to
big
put it,
difference.
Joe, is like the teach yourself with an instructor's assistant, because you have all of the materials, but you have to, you're learning at your own pace. And often, like when you get stuck, you have to reach out. And if it's after hours, like, you're waiting until whenever to fix your problem. So it's like that. I've done both versions of school. And for me, as like a person with like ADHD, I really enjoyed being able to like rewatch videos and really just like take in the information. But there's a lot to be said when you're in person and you're getting to see examples worked out right in front of you, and the knowledge that you get to take away with that by just being able to ask questions in the moment and hear other students' questions, because they might ask something that you didn't even think about that ends up helping you solve a problem later.
One thing about the immersive though is it's 17 weeks, 9 hours a day. and you can only miss 3 days. If you're kind of person who learns that way, it's perfect. Everybody finds the program that fits their learning style. Immersive is amazing, but it's 17 weeks of hold on.
Yeah, and that's
Yeah.
the New York area or the Denver area, right? Like right now it's New York, and then next year it will be
Just
Denver
New
as
York,
well.
I think,
Yeah.
for data science.
Yes, until the
Yeah.
until the end of the year it'll be just New York.
Oh, really? Just New York? I'm
Yeah,
kind of
it's
lucky.
just New York for right now.
I'm
Yeah.
kind of lucky, but
So we have a couple of questions I want to address. One was Ruby was asking about it never hurts to take courses on Udemy and things, especially if they're free. The more that you do before you get here, the more it'll help you, but it's not required. Probably about 10% of our students are actually teachers who have no coding experience. They're just tired of being in the teaching profession and want something new. So the course is built for people with no experience. And then Sumi, if you have a lot of questions, then in person is probably better because you have an instructor and students there at all times helping you for the 17 weeks. And is it Barbara? I think you would do great here. R is awesome. Python is better for data science, even though the R people would cringe at me saying that.
Absolutely.
R is a very niche language, and its users are absolutely fanatics. And you can get jobs in R, absolutely, but there are many more jobs in Python. And the thing about Python, if you come here and you take Python, okay, you take the data science, you'll be eligible to apply just for simple Python jobs. If you love Python coding, you'll be available for data analytics jobs and data science jobs. So, whereas R, you're not really available to be a programmer. You are available to do R and be a data analyst and a data scientist, and that's it.
So I dropped a
Yeah.
link in the chat, just if anybody wants to learn more about the programs and talk to the admissions team and just like get more information, that'll be on October 19th at 8 p.m. to 9 p.m. Eastern. And they are the most knowledgeable, I mean, other than instructors and students, about just like all of the nuances about each of the different disciplines. So if you're not really sure like where you fit or whether in person or flex is like the better way to go, it's always great to just like pop into these info sessions and be able to chat with the admissions team because they know the programs like just in and out.
So Sumi, the thing about the flex is it's 20 to 60 weeks. Of when you finish it is up to you. You can finish it as soon as 20 weeks or as long as 60 weeks or anywhere in between. So by the time you wait to next summer to do in person, you could be finished the flex. And I'm not pushing flex. I'm just, giving you an idea of how to do it. I think no matter which of the programs you're in, it's an amazing opportunity. Think about it. For the cost of this, you can totally change your life. In terms of your future. There's so many jobs in data science right now because it's just everywhere. It's in medicine, it's in media, it's in sports, it's in meteorology.
I was like, I think it's harder to find
everywhere.
Somewhere that where they're not using data science at this point.
Yeah, data science is definitely
data science.
Yeah, it'd be hard. There are too many things I can think of I couldn't use data science for. You can use it at the zoo, to get ideas or how animals are going to fare in certain biomes. So definitely in healthcare. And
somebody said healthcare insurance. Yeah, healthcare, there's so
absolutely.
many data science jobs in healthcare. Like so many, so many. But I'm not interested in healthcare. But
data science was slow to adapt data science.
Yeah.
So I taught the Python part of what you saw today at Camden in London, and I had 5 docs in it because they're trying to understand how this stuff is all changing and what's in it.
Yeah. So it's
So
really good to like, especially if you have a specific interest, like depending on what type of project you want to do. Like, I've done projects with, using images to detect, certain things, or I created a recommendation system. I've done, whether customers are going to churn from a company or not. So like, there's a lot of things you could do with data science. I've seen all different types of projects like predicting stock markets, or, I've seen like COVID analysis, and like there's so many different things you could do with data science and so many different fields you can enter. And there's just a lot of interesting projects out there that you could take on, and it's just fascinating and exciting, at least to me. I just find the idea of solving problems really, really fun. So, and then data science allows me to like, go for that and go headfirst to try to solve that.
And with all this talk about Python, the next event we have for data science is going to be at the end of November. It's going to be on the 30th. And it is going to be Intro to Simulations using Python. So if anybody wants to learn more about Python, that'll be an excellent event to attend. But we are at time unless anybody has any last minute questions.
I just want to tell Sumi it'd be absolutely okay for you to take it in person. And where are you, Sumi? If you're in New York, I know the instructors in New York, and none of them will be condescending to you. Jonathan knows them too.
I definitely know. Praveen is my guy.
Oh, I love
Praveen is my guy.
Praveen, I was Praveen's coach for a little while.
Oh, you're not in New York. Where are you at, Sumi?
Joe Mata too is cool.
Oh, you're in Georgia. Okay, yeah.
So Sumi, there is another version. Okay, there's the 17-week in person. There is a 17-week course in Zoom. That's exactly like the in person. You just do it on Zoom. So you can do that from
program,
Georgia.
right? Yeah.
Thank you. I always forget the name of it.
I was like, live flex program. Okay.
Yeah, live. So
yeah, and we are and we are fully licensed in Georgia. We actually have had campuses there previously. But yeah, there is a way to do it in 17 weeks. But it's committing to a full-time job pretty much. And I think I learn better when it's all crammed in a short amount of time. I just feel like when you're just inundated with something, especially like this, it's like learning a new language. So the more you're around it and interacting with it, the easier it's going to be to catch on.
Yep. And Sumi, those start every month. So there's a new cohort in the online live starting just about every month. And I know a lot of those teachers. They're pretty cool.
I like the entirety. I mean, I like all of our instructors, but I really love our data science team. I think they're pretty amazing.
We're a little weird, especially Praveen. Wherever it is, he knew I said that.
Oh, Sumi, you're asking what was that again? Are you talking about? So it's called Live Flex, I believe. Right. So that's where the admissions team is like the best people to talk to, because they know all of these little like pieces.
Corey, what are you calling it? Live?
Like it's
live
like a
flex.
I think it's like
so there's the live program, and there's live in person and live online.
Yes.
Live in person is in New York, where you go to a classroom. Live online is on Zoom. 17 weeks, 9 hours a day. Just instead of being in person with an instructor, your instructor is on Zoom the whole time. But it's exactly the same as in person.
That's true.
Everything else is the same.
Yeah, I personally prefer like this boot camp experience personally, because I've been to traditional school, like college, and like I feel like I don't know, for me, being in the boot camp gives me all the information I need to know in a more condensed time, compared to like, when you go to a university, like it's like you have to take history and all that. I understand it makes you a well-rounded individual, but I just kind of wanted to go to school to learn whatever my major was, rather than focusing on all the other fluff. So like the boot camp kind of cuts the fluff out, and like, and just lets you focus on what you need to do.
You can do this part-time with Flex, Joseph.
That's the idea kind of the Flex. It's kind of part-time.
It's at your own pace. Whereas the live programs are going to be, that's your 45 hours a week.
Yeah, it's a lot.
How much of the boot camp applies to real world scenarios? I mean, that they're teaching you enough stuff to get you, and you at the end of it, you know, or through the, when does career coaching start? That's the part that I always forget. But you get partnered up with a career coach and they help you find work. That's like, that's one of the things. So like when you leave the program, you should be able to get a job in data science. Like that's the whole point behind it.
For like real world scenarios, I would say for the most part, it covers a lot of it. But the thing is that there's also still like with data science is such a wide field. So depending on what field you're going to get into, you're still going to have to learn a lot more because like, for example, like right now, my primary interest is like, you know, machine learning neural networks. Like I like that type of field. So like one thing that I have to really brush up on is my SQL because my primary focus was like Python, and we do SQL, but like there has to be more in-depth knowledge. And like Eric said, like presentation skills, you present every single phase. So it also helps you learn how to break down data much better and makes you a much more presentable person. So like if you were to do a presentation for somebody, it would be very applicable. And understanding that, you know, when it comes to like, I think that when it comes to the projects that we do, like the actual application, like how Joe went through everything, you would probably do that in real life. It's just, there's a lot more data in the real world is a lot messier. So like probably your data cleaning and your like analysis is much more in detail. But in terms of machine learning and such, you will have pretty much the foundations that if you were to get hired at a data science company, you would, I mean, if you get hired at a company as a data scientist, you'll be able to hold your own for like, at least for the most part.
Absolutely.
Yeah, there's always a learning curve when you start in a new role in a new company because everybody does things their own way, but this gives you the foundation for what you're going to need in the real world.
Yeah, and different companies use different tools. Yeah, like some companies like to use, for example, like you could use like cloud architecture. There's I mentioned Google Colab earlier, but there's also Amazon AWS, there's Snowflake, there's Redshift, there's so many other tools that different companies use. But I think the most important thing to understand is when you get into a data science program, the goal is to learn how to learn. So when you learn how to learn, then whatever tools you need to use, you'll be able to adjust quickly to it because you're so used to it. Like being in a boot camp like this, like you have to figure out the most efficient ways to solve problems and what tools you need to use. So you have to learn the tools quickly, be able to use the tools in an effective way and understand the tools that you're using. So if you're learning how to do that, when you go to a company and they say, oh, we use these tools, then all right, cool, I could do that. Give me like a few days, I got this tool down pat. You know, like because I mean we're learning Python in like a week, so they can't tell you anything. Like if you're learning a whole language, you know, or you're learning about machine learning in like 2 weeks, there's not much they could throw at you that's going to be like too crazy that you wouldn't be able to handle or adjust to. So yeah, there's a lot of tools that different companies use. But a lot of companies also use open source tools like SK or use Python packages like sklearn. Like for example, I was talking to a cohort member yesterday, and he was telling me that he went to a meetup with a Spotify data scientist, and they were talking about like how they do their data science. Everything they use is Tensorflow, and Tensorflow is something that we learned at Flatiron. Like at least I like Tensorflow, but like they use only Tensorflow for their databases and things. I mean, to extract from their databases and to do their machine learning. So if I know TensorFlow, so if I were really working at Spotify, I wouldn't be like, oh my God, what am I doing? Like I'd be like, all right, cool, I got this. I could do TensorFlow. There might be a lot of nuances to the TensorFlow, but I could adjust to that. It's not like I'm just going in blind and not knowing TensorFlow at all. So.
Well, thank you all. I'm going to let everybody go home. We've gone a little bit over, but I just think that the conversation was amazing, and I wanted to make sure everybody's questions got answered. We really appreciate you spending the evening with us and learning more about data science and more about Flatiron School. And we look forward to seeing you at another event. Thank you again to Joe and Jonathan and everyone else, and have a wonderful night, y'all.
Thanks, Jonathan, for helping out.
Yeah.
Joe, as usual, You're the man.
Jonathan's my buddy.
Bye, y'all. Have a good
Cool.
night.
Good night, everybody.
Good night.